Right. Good afternoon, everyone. Thank you for coming to this event. Today's guest lecture series will be delivered by Professor Rachel Cardell-Oliver. She was my supervisor at the UWA. The title for today's guest lecture The title for today's guest lecture is Accurate, Cost-Aware Fault Tolerance Monitoring with Minimal Sensor Infrastructure. But before we start the guest lecture, let me read through her curriculum vitae first. Yep. Professor Rachel Cardell-Oliver. She graduated from UWA from 1980 to 1984, and then her master degree was also from the UWA, 96 to 86 to 87. I'm sorry, and then her doctoral was in computer science from the University of Cambridge from 1988 to 1991. Her research interest is smart meters, sensor networks, water use, object-oriented programming, monitoring, soil moisture, earth, wireless sensor networks, and many more. These are some of the research interests that I got from the UWA repositories. This is her contact number, and it is actually the office contact number. It's not her personal contact number, and her email. So for those who are interested in her research, you can just email her if that's okay, Professor Rachel. Right. That's that, and then I would like to play the video of the UWA before we commence to the section. Right.
Our motto, Seek Wisdom, is as relevant today as it was when our university was founded more than 100 years ago. Here in Western Australia, we are Australia's gateway to the Indian Ocean Rim and beyond. We have deserts behind us and the world ahead of us. We will bring together outstanding minds to solve the world's most complex problems.
In Seeking Wisdom, UWA has outstanding talent focused on solving real-world challenges, now more critical than ever to our planet and our people. A collaborative approach to education will create the next generation of leaders through experience-rich education and world-leading research. Our research will advance healthcare, economic development, environmental improvement and social justice, here, across our region and around the globe. We'll take every opportunity to work across boundaries, become a driving force for positive change, and advance the prosperity and welfare of our communities. And we'll achieve this by partnering with organisations that share our vision. Together, we'll have the power to build our future. Join us as we launch UWA 2030.
Yeah, that is a kind of introduction to the UWA University, where I spent 4.5 years, Professor Rachel. But that number, yeah, was very meaningful for me during my PhD study. Right, now we can start the talk from Professor Rachel. Please, Professor Rachel, if you'd like to share a video or sorry, your screen.
Can you all see that?
Yes, we can see that.
Okay, can you hear me? All right, well,
yep.
Thank you very much, Ari, for the kind introduction. And also thank you very much for inviting me here. When Dr. Shiddiqi invited me, I said, oh, I would really love to come because I'd love to visit Indonesia, but we're not allowed to travel at the moment. And he said, no, it's all right. You can do it online. So here I am online from Perth, but I very much hope that maybe some other time in a few years' time, I might be delivering this lecture face to face. So thank you for joining me. It's great to have the audience. If you have any questions or problems, Ari, are you able to monitor the chat
Sure,
as
I
we
will.
go? Yeah, so
Yeah.
he'll let me know if there's any, or you can turn off your microphone and turn on your mics and interrupt if you've got any questions.
Yep.
Okay, so as was said in the introduction, I thought, because we've got an hour and a half, that I wouldn't just talk at you for that long, but I would divide this talk into 3 parts. So the first section of the talk, which is quite short, I'd like to introduce you to my research field, which is wireless sensor networks. I'd then like to go into a more technical session describing a particular technique that I'm very interested in called virtual sensing. And finally, it's always fun to look to the future. So wireless networks is a field that has changed really dramatically and really fast. And I think the next 10, 20 years, it's going to change really fast and really dramatically again. So I just want to do a little bit of future gazing. And I hope maybe inspire you a bit to think, you know, this might be a topic that I could work on or find out more about. So those are my goals for today. Okay, so here's part 1, which is the introduction. So I'm going to start with a picture which actually comes from 1955. This is a book that belonged to my father, and then it belonged to me, and I really loved it. And it was basically a history of mathematics. And the book is called Man Must Measure. And I took that to mean woman can measure as well. And man has always wanted to measure things from very ancient times, and you can see in this picture various places where people have made sense and managed their environment by measuring, by in various ways, by taking measurements from their environment. And wireless sensor networks is a step in that journey. So what's in a wireless sensor network? Well, the first, as the name suggests, so what is a wireless sensor network? What I mean is a distributed system comprising a set of sensors that's measuring some sort of environment. And that environment could be a field or a forest. It could be a building. It could be a person. It could be a city. The characteristics are there are no cables. So that's what wireless means, no wires. So the communication in this system is using radio waves, and there are many technologies for doing that. Okay, so we've got a set of distributed things, sensing, and somehow they're working together, they're communicating wirelessly to achieve some aim. So let's have a look at each of the parts. I'll come to sensors, but the technology drivers for this are that the world is changing, as I said, changing very fast. So sensors are becoming much cheaper and much more widely available. There's a lot of change in communication technologies from Bluetooth, radio, mobile phones, etc. And again, those are becoming cheaper and cheaper over time. There's a lot of options for collecting, storing, and sharing the data now. And because all this technology is becoming mainstream, it's enabling more and more people to experiment with measuring devices from wireless sensor networks. So what do I mean by sensors? Here are some of the sensors that I've used in my work. A lot of my work is environmental, so you'll see lots of fields in my talk. So these are soil moisture sensors. This one is a temperature sensor. That's one of the simplest and smallest sorts you can buy. This one's rather interesting. It's measuring the sap flowing through a giant tree, a rain gauge, etc. All of those are the types of sensors we might use in our network. The next part of a sensor network is a microcontroller. And here is an example of various microcontrollers that have become available over the last years. So this one is called the Mica 2 Mote. It came out of the University of Berkeley in 2002. And that was one of the first ones that researchers could buy and do experiments with. Here in Australia, the CSIRO came up with a similar system called the FLEC. Probably in your classes or in your hobbies, some of you are using Arduino devices or Raspberry Pis. So you could see, you know, an Arduino or a Raspberry Pi, you can go to any shop and buy one and play with it. So this technology is becoming mainstream, and that means that anybody in your class, in your hobbies, people are doing it in primary school, you could build a network using all these components. Those get put together. This is one I built in my garage. It's a sensor node, so you can see in there the microcontroller. It's connected down here to some sensors that you can't see. And this was part of a network of nodes that are gathered together, sensing the environment and relaying the information. So there's a picture of it put all together. So you've got sensors in the field. They communicate with each other wirelessly and send information through a gateway. That information can be stored permanently in the cloud or in a database somewhere. And then we can have web access. That data can become widely available. Ultimately, so whenever you're thinking about software, software is only there to solve people's problems, to make something that people do now go better. So when I think about sensor network software, I think in one side I've got users and they've got some questions. So these are some farmers with some questions about their farm and maybe the soil in their farm. We've got the technology and environments, and the sensor technology is there to answer questions. So maybe this farmer wants to know whether to stop watering or whether to stop fertilizing. So where these sensor networks come in is we can gather the data that helps them make that decision. So as far as building a system, what are the system requirements for doing that? Well, the measurements need to be accurate. Okay, there's no point taking the measurements if you can't trust them. So we need to make sure we're able to monitor these complex spatial temporal phenomena. The system needs to be fault tolerant. Okay, if you're going to take a computer and run it in a natural environment in the field, it needs to be able to be set up and adapt to a changing environment. Again, if you're going to take it away and put it in a field, it needs to run pretty much by itself. So typically nodes are battery powered. You might have noticed the battery in the example I showed you earlier. Or in future, nodes could actually harvest their own energy. So from solar energy or kinetic energy or temperature differences, so that the nodes can run by themselves without needing a lot of attention. And then fit for purpose. So fit for purpose is where we balance all those things, because you usually can't have everything perfect. So what they need to be is sufficiently robust, sufficiently reliable, sufficiently cheap, sufficiently fast, sufficiently self-maintained, sufficiently scalable for the particular application that you're building. Okay, the reading for this, I've sent the slides to Professor Shiddiqi so he can show you afterwards, but this is a really good introduction to the way people build sensor networks, and it actually describes the sensor network that we built in this field. In fact, if you look very carefully, I think that little line is an antenna that we deployed in the field. Anyway, that's a good paper for an introduction. So that brings me to my first set of questions. So I wasn't sure if you'd have questions. I hope you do, but I've got some for you too. And my questions are, why is the wireless important in wireless applications? Why is it important that it's low cost, they can be built from low cost and easily available hardware? And I hope that as I've been talking, maybe you've thought of a way that you could use these, a wireless sensor network. You've thought of something you could use one for. So would anybody like to jump in with any of those, or I'm happy to answer any questions you might have.
All right, if there's some students who would like to answer. Oh, by the way, Professor, we've got our dean here, Dr. Ketut.
How do you do?
Fine.
Thank you for joining.
Yes. Thank you for giving us lecture. Thank you. Bye.
All right. Yeah. Anyone would like to answer the question from Professor Rachel? Why is wireless important for WSN applications? Second is, what is the importance of low cost, easily available hardware cost for the WSN, etc. Anyone who would like to answer the question? Yeah. Anyone?
Everyone shy.
It's a warm up for them, Professor Rachel. So that's.
So in your city, can you see, around your campus, the things that you might be able to do with one of these wireless sensing systems? Do you have any in your campus that you know of?
Yes, actually, we have a green field. Yeah, green field.
Okay.
Yeah.
Yeah.
For,
Are you doing some monitoring on that?
yes, yes.
Oh, great.
Mm.
We have also a space. Yeah, actually, it can be also planted with many kinds of plant. Yeah.
Excellent.
Yeah. I think that's good.
Yeah, I think that's. Why is low cost important, do you think?
Because we need many sensors to be planted on the ground, on the
yes.
field.
You mean many, and if they're commercially available, it means that anybody can go out and buy them. So a farmer could set one up. But otherwise, when I started in this field, only specialist researchers could do it, and you needed a PhD student to program them. But now there's much more. It's much more accessible.
Great.
Okay, last chance. There's a prize for asking a question.
I hope the prize doesn't fall to me. I'm the person who is going to be delivering the prize. Yeah. Anyone who would like to answer the questions? Two questions.
Right.
Ask one. We've got one here.
Excellent. Thank you. Baskoro, is that how I say it? Is it virtually impossible to set up a wired network in a rural area or the nation? It is indeed. That's exactly the problem. So there are lots of places where it's simply not feasible to use wires. There are places where you can, but if you want to be outside or in the ocean, then you have to be wireless. Good. Thank you very much. Okay, I shall move on. So the second part of my talk, I want to talk about one of my favorite ideas, which is virtual sensing. I'll start with a bit of motivation. So about a few years ago, I was involved, I was one of the investigators on a research project, which was for energy saving rammed earth buildings for remote housing. And the idea was to build houses out of rammed earth. You've probably seen this in your country too, where the house is built from blocks, just from the earth that's available on site. And these we thought would be suitable for outback Australia, so for Aboriginal communities living in remote places, because it's very easy to build. You build with material that's readily available on site. But what people didn't know about rammed earth was how well it would perform in arid places. So if it's very hot, is it feasible to live in one of these houses without air conditioning? Will they keep people cool? So what happened in this project was we had some money. The Department of Housing built 2 houses, and here they are, in a city in Australia called Kalgoorlie, which is gold mining. It has the largest gold mine in the world, I think, the super pit. And we built these 2 houses. One of them had insulation in it, and the other one was just straight rammed earth. And what we did was we put a sensor network into these houses, literally into. Some of the sensors were going inside the wall, and other sensors were placed in the room. So these little dots in the diagram show you where the sensors were placed. Okay, so that was the project, and the idea was to collect information, to measure the performance of those houses, to start getting some scientific evidence about how they behave, so that places like the Department of Housing could make decisions about whether to build thousands of these houses or not. So here's the sort of data so there's a bit more of a close-up of the house. So very attractive as well as being cool. And here's some of the data we gathered. So the color, the blue and reds, that's actually the sensors that were embedded in the wall. So you can see there a temperature profile across the wall. And then we've got how this one here is inside the house, telling you what the temperature's like. There's an example of the sensor that we embedded inside, going right through that 30 centimeter wall. Okay, so far so good. We collected a lot of data over a year and a half from 2 houses, so there were several hundred sensors. What's the problem? So the problem is managing several hundred sensors, buying several hundred sensors, maintaining several hundred sensors is really hard work. And I was actually the person that did a lot of that hard work. And so that prompted me to think about, could we do the same job, so the same information, but with fewer sensors? So the question I asked was, can we take some of the sensors out of the wireless sensor network and replace those sensors with a software model? And I'm going to tell you now how we did that, but just so you all start happy. The answer is actually yes, you can do that. The reference for this is a paper that we published at the end of this project on how you could do that with a system called Build Sense. So you can look that up in ACM transactions on sensor networks. Now here's what's in the paper. So the idea is something which we call sense, learn, predict, monitor. And it works like this. So you start by deploying lots of sensors, more than you think you need. They're temporary and semi-permanent. So you could buy some cheap, off-the-shelf sensors and deploy them in the house. We had some hanging from the ceiling, and they were obviously, you can't keep those running forever. And during that semi-permanent, during that first phase, data gathering phase, you collect lots of data from the sensors into a database. We then get into the learning phase, which is when you build the virtual sensors. And this is basically a machine learning phase. And you select from that permanent sensors. That learning phase is making questions about, is the sensor, is it adequate? Is it feasible? Is it fit for purpose? So you might go around that loop a few times. Once you've finished, you just deploy minimal permanent sensors in the building, and you use virtual sensors, where a virtual sensor is a sensor that's predicted. And from time to time during operation, you might need to update that system. Okay, so that's the whole paper in a 1-minute nutshell. But basically, we're combining machine learning with sensor systems. So the steps, those are the 3 steps. You gather the data, you do the learning, and then you monitor a long-term deployment. And I'll go through each of those steps, a little bit of detail. So first, the data gathering phase. You deploy the temporary sensors and you gather that data during a training period. And here's another example of the ones going through the house. So here the blue is the outside temperature, and you can see that's going up and down a lot. And this red one is the temperature inside the house. And you can see that that's remaining pretty comfortable. And that's exactly what we wanted. We wanted the house to moderate the temperature. So that's an example of the type of data we collected. We're then going to use that data to learn soft sensor predictors. So maybe you see how these green and the black ones are very close. Maybe we only need one of those sensors. And then we remove the temporary sensors and deploy the physical ones. So here's how we learned it. There's lots of ways you can do it. But here's the problem statement. Suppose you've got 2 sensors, SI and SJ. And each of those are reporting a time series of, let's pretend they're real values. Okay, so maybe it's temperature, and they're reporting temperature every 10 minutes or something like that. The aim is to learn a function, this one here, F, so that for all times, sensor I at time t is equal to this f function of sensor j. So if I know sensor j, I can apply this magic f function and I can get the value of sensor I. So sensor I is what we call a virtual sensor, because if I have the measurement from sensor j, then I can calculate the value at sensor I. Okay, and we learn that f from training data. And there's lots of ways you can use it. So the simplest is some sort of regression or correlation model. And then there are more complicated ones. We're working on some of these at the moment, like neural networks or deep learning. It turned out for this data that a fairly simple regression worked. And what we did was we found that there was a regular daily pattern. And if you took that, and you could see that here in the red, if you took that daily pattern plus an offset, you could very well predict one sensor from another. So we call it the nearest hour of day predictor. It's not clever in itself. It's just pretty exciting that you could actually do this with such a simple predictor. And it turned out that a really high proportion of sensors in the whole system could be predicted that way. So we were able to get down to about 30% of the sensors we initially had. Okay, so that's the learning part. It's useful to do a little bit more than that. So I'll tell you a couple of other problems. Firstly, let's have a look at the selecting. So suppose we do that process, we learn an Fij function for all the possible sensor pairs. So we've got 100 sensors, we make a matrix of 100 times 100, train that 10,000 models, and have a look at which ones would have good enough, so sufficiently accurate predictors. Those are our candidates for virtual physical sensor pairing. We then use an algorithm called minimum set cover. So minimum set cover is a way of working out what's the smallest number of physical sensors I need to cover to be able to predict every one of the virtual sensors. And then having used that algorithm, we can partition the sensors into physical and virtual. And we do that with a number of constraints. So one constraint is accuracy. There's no point doing this if you're just going to be predicting rubbish. So we need to know that the prediction, the function that we've learnt, gives you sufficiently accurate predictions. The cost needs to be minimized. So normally that would mean the smallest set of physical sensors, but you could also build in the cost of the sensors, because some sensors are very expensive and some are very cheap. So maybe you want, so you could actually do that as a dollar cost. And the third thing that we want to build in is fault tolerance. Now, the cheapest solution might be one physical sensor predicting each virtual sensor, but then you haven't got any tolerance. So if something goes wrong, you've actually lost two sensors. So what we can do is have multiple sensors predicting each virtual sensor. And then if one physical sensor fails, we've got another one to take over. And because sensor networks are built of cheap, low-cost parts, and they're deployed in challenging situations, they do need to be fault tolerant, because there's a lot of things that could go wrong. So we built that fault tolerance too. And this graph on the right shows you how we make that decision. So we tried a number of configurations, and the black line, for example, tells you the fault tolerance, how many predictor sensors there were. The red line tells you the prediction error, okay, which is on this axis. So all of these solutions have a prediction error less than 2 degrees, it was in this sense. The blue one's fault tolerance, and the black one is cost. So the more sensors you have, the more the cost goes up. And then we use a technique called Pareto, a global Pareto front, to select a solution, okay? Because there's multiple solutions, multiple ways you could choose your physical and virtual sensors. And the problem itself is NP complete. So we need to use some, or NP hard. So we need to use some heuristics to find find a solution. Sorry, I keep jumping ahead, more slides. Controller's a bit strange. Okay, so that's the train and select process. The last question you might ask is, I told you we were going to train these for a short time. So the idea was, in the house, for example, you'd have sensors in for about a month. You'd take lots of measurements, you'd go away and do some machine learning, and then you would do some permanent measurements. But I hope you're saying, but how do you know that those predictions are still good down the track? So maybe they wouldn't be so good in winter if you trained in summer, or maybe they wouldn't be so good when things changed. That's a very good question, and it's something you definitely need to think about. So the solution we thought of for that was something called Sentinel Sensors. And what those are doing is giving you extra fault tolerance. So what a Sentinel is a pair of physical sensors that can predict each other. And what you do is you run those predictions of the physical sensors to see whether they're accurately predicting each other. If the prediction starts drifting or getting inaccurate, then maybe something's changed. The environment's changed or your predictions are not good. So if the things you can see are not predicting accurately, it's quite likely that the things you can't see are not predicting accurately. So if that happens, if the Sentinel suggests that there might be a problem, then what you can do is check for changes and you can consider a retraining phase. Right? So sometimes you might need to retrain the network. We did some experiments to see how well that would work. And actually we found the network was surprisingly stable. So each of these is for one sensor. On the left, these are the errors if we use the whole data set for training. Okay, so not having a training phase and an unattended phase, we just train. So this is, if you like, the best case. This is the best predictions we could get. If we trained just in November and April, or just in November, or just in February, so we just used 1 month of training data, you'll see that the results are really quite similar, certainly for this sensor. And so these are all examples of training for just once or just twice, and we'll find they're pretty close to the best possible. And that happened for a number of different sensors. So, but not all of them. So here's an example where this is the best we can do. And if we only use 1 month for training, sometimes the predictions are very much worse. So here's an error of 15 rather than 8. So you have to be careful. It doesn't work for all sensors, but you can use the Sentinels to tell you whether you've got one of these good cases or a bad case. So that's rammed earth houses. Now, to a certain extent, that example wasn't too hard to predict because we were measuring temperature and humidity mostly, and those things are relatively easy to predict. Here's an example that I'm working on at the moment, which is very much harder from a prediction point of view. So this is a novel wastewater treatment plant, and the goal of this system is to take wastewater, so water from your toilets, from your household, or from factories, and transform it into saleable products, but also treated safe water that can be used for irrigation. The technology that we're working with, I'm not doing this, this is our partners at the University of Queensland, uses a biogas, a treatment, a high rate anaerobic treatment that first processes the data. And then the data from this treatment, so this is done in a tank, that produces biogas. And then that's sent to an effluent, an algae pond, where algae is used to further treat the water. That algae can be harvested and is itself a saleable product. And the treated water is then safe to use for irrigation and things. So this is a new technology. It's got its benefits of things like low solids, better light, healthy algae harvesting. From the sensor network point of view, what would be the benefits of virtual sensing. So in order to measure this, imagine you're placing sensors, chemical sensors and physical sensors all through this system. Okay, so they're placed in the algae pond, in the biogas, etc. Some of those sensors are very expensive. So for example, one of the things you want to measure is ammonia. The sensors for measuring ammonia cost $20,000 or so. Another thing you want to measure is cell count. But cell count tests have to be run in a lab and taken away, and they take a week to do. So could we build some virtual sensors for this system where the benefits are really high? The problem is that the processes here are much more complicated than the relationship between temperature sensors. And so the technique we're using here, are we building deep learning models for learning how to predict cell count or learning how to predict ammonia. This is actually work in progress. We're doing this work at the moment, but the initial results are looking very promising for that technology. So I think there's lots of possibilities for this idea of virtual sensing. So for combining sensor networks research and machine learning research to build much more cost-effective and reliable systems. Which brings me to my second set of questions. So virtual sensing was about minimizing the number of sensors. I hope that you've all got an idea from what I've talked about why you might try and minimize the number of sensors. I hope I gave you some ideas about why fault tolerance is important, and also why you need to monitor long-term. So why are sentinels useful? I don't know if anyone's been able to think of a case where those predictions might change. Anyway, there's 100 of you, so I'm very much hoping somebody has a question. Are you awake?
Come on. It's an open challenge from Professor Rachel to everyone. I think the three questions, the answer of the three questions has been delivered by Professor Rachel in her talk. So yeah.
Ask me another.
So please, anyone who would like to answer the questions, anyone, you can raise your hand, or maybe you can type in the answer on the chat room. Yep, if I'm mistaken, the Sentinel concept, I think it has a similarity with the one that the paper in my reference, it was from Wasim Abbas that used the minimum set cover as well, minimum set cover algorithm, where two sensors are complementing each other in order to, for example, if one sensor fails, then the other can take over the role of that sensor. So that set of sensor needs to be able to cover at some range to be able to cover each other.
That's exactly right. In fact, I should have included because your research work is also, your PhD research is also related to this, where we were looking at the optimal place to place sensors for leak detection.
So I remember that the 100 by 100 metric is similar to the influence metric that I use for my thesis. All right, anyone who would like to answer the question from Professor Rachel? 3 questions. Anyone? Okay, Mahar, are you here, Mahar? Oh yeah, by the way, we've got Annie and Lenny. They're both supervised by Professor Amitava. It was in 2008, if I'm mistaken. Yes, Annie and Lenny.
Oh, great. Oh, hi, Lenny.
Do you remember Lenny?
Yes.
Yeah, she's here, I think.
Great.
Yeah. Right. What should we try to minimize the number of sensors in WSN deployment? Anyone would like to answer the question? I think it's something to do with the cost, Professor Rachel, if I'm mistaken. Yep, the cost. For the second question, why is fault tolerance is important to for build sense? If I'm mistaken, that it has something to do with what do you call it? If one sensor fails, then the other sensor can cover the role of the sensor.
That's right, because you're likely to have sensor failures, so you need a recovery.
Yeah. What about bias sensor, Professor? Is there any? Yeah.
Question, Ari, you win the prize. Okay, yes. So a sensor might be biased. It might be consistently giving the wrong results. So that's where the sentinels come in. If the sensor's biased, if your initial readings are wrong, then, and you don't know that, then you've got a problem. But if a sensor starts drifting over time and becomes biased, then hopefully your sentinels will pick that up, because your predictions will start to be wrong. So the sort of case, I can tell you some of the cases that came up in the house. That's right, to make sure they could be used for a long time, because good, that's alpha, good. Yeah, so because situations are likely to change. So for example, in the house, maybe a tree grows up, or maybe somebody builds a house next door, then your original predictions might be wrong. We're talking about long-term predictions here. Or potentially when the seasons change, you probably want to make sure that you are robust to that seasonal change. So there's lots of ways that the natural environment might change over time, and you might need to rethink your sensors. Okay, thank you very much for your answers and your questions. I think in the interest of time, I think I'll continue, because now we're going to do some future gazing. So I hope I've interested you in the sort of possibilities of this technology. So what I want to do now is tell you some of the sorts of problems that people are looking at for sensor networks, and some of the exciting areas that I hope maybe some of you will be working on in the future. So the first one, you actually saw a picture of this. I don't know if you remember, but there was a picture of this in the video that Ari showed you of the University of Western Australia. This is our future farm. And this is my colleagues who, this is my German collaborators, my friends and a colleague here at UWA, and there's me at the future farm. And this is one of the sites where we are doing research on future sensor networks. So there's a lot of measurement devices here, and indeed, under the ground, there are some special sensors that we inserted. So in this enclosure is a sensor with a special type of radio that can transmit through the ground, and 4 to 8 soil moisture sensors. So you can just see the soil moisture sensors sticking into the soil there. And at the top, you can see a graph of the sort of information we're getting from that, from those sensors. And on the left is a map of where the sensors are buried in the field. So the idea here is, on a farm, it's not actually very convenient to have sensors sticking up above the ground, because you need to drive tractors, you've got sheep, you've got an Australian farm, you've got people shooting things. So you need to, if possible, if the sensors can be out of sight, that makes the network much more robust and better able to run to the future. So that's one type of future research. How can we make the sensors more invisible? So hidden away so they can look after themselves, so they're not interfering with whatever it is that you're measuring. So that's one. Underground sensing is one of the future areas I think is really interesting. This is another example of underground sensing, but it's taking a slightly different approach. This is saying, instead of collecting the measurement at the sensor and sending it back to the base station, maybe you could use contactless sensing. So think like an RFID reader or a Bluetooth tag checker. The tags could be inserted in the soil, and then you could use this special reader to interpret the signals from the tag and calculate what the soil moisture is. So this is really a signal processing problem. And there's work going on this for farming applications from Colin Josephson, who's a researcher at Stanford University. There are also applications of this for, one of my favorite examples is one for reading a 3D printer. So you can use your smartphone to listen to the sound of a 3D printer. And if you do smart signal processing on the audio signal, you could actually work out the movements of the 3D printer. So I think contactless sensing, so sensing without actually being in contact with the thing you're interested in, is a really interesting future area. And one of the interests in that area is body sensing. So on the left is an example of a traditional body sensing setup for measuring sleep behavior. And you can see that this poor guy's got lots of, obviously this is hand up, but he's got lots of sensors attached to his body in order to monitor his sleep pattern. What this group from the Massachusetts Institute of Technology did is they used signal processing on Wi-Fi signals to try and learn the same information. So this is another example of measure and then train. So you measure using the contacting sensors, and then you see whether you can get the same results by signal processing on the Wi-Fi signal. And they actually got very good results with that. And there's a lot of work on analyzing Wi-Fi signals to monitor body, things like heartbeat, movement, sleep patterns, etc., without having to attach sensors to people. Here's another example of that you could use for room monitoring. This is a thermo sensor that we developed here. It was a project at the University of Western Australia. And the idea is that you can monitor occupancy in a room in a way that protects people's privacy, but gives you good information about people in the room. So that was the on-body networks that you saw. So these are used in hospitals, emergency, etc., where we get a lot of information from a person. They're also used for aged care. You can go further than on-body sensor network, and that's an in-body sensor network. So it's now coming possible to have micro smart pills that include a transmitter that can send information from within your body about the what's going on. So these could be used to track digestive problems. They could be used for controlling drug delivery at the right places, and for various sorts of treating diseases. I think in-body networks is a really interesting area because there's actually quite a lot of ethical and emotional things about that. I wonder if when I said that you thought, oh, yuck, I don't want a sensor inside me. I don't want somebody monitoring my insides. Or maybe some of you thought, oh, wonderful, that will be great for medical applications. But people tend to have a very emotional response to that because, you know, it's really the most intimate sort of sensing you could do. So I think that's a really interesting area. And microsensors. So this is another CSIRO project where they built a sensor that was small enough to put on a bee. And then these bees flew around with the sensors and they collected a lot of information about the way that the bees were sensing. So microelectronics, nanoelectronics are providing ways that we can make these very small sensors, and that opens up a whole lot of new application areas. Okay, so at 3 o'clock, that brings me to the end of that. Oh, no, it doesn't. Sorry, there's more. Okay, so they're the different types of sensing technologies that might change. The other thing that is looking to the future, but beginning to become possible even now, is instead of using radio wireless waves to communicate, perhaps you could use visible light. So you could actually use a standard light emitting diode to transmit data. And you can do that at, so imagine a flashing light in your ceiling, but you can do that at the rate where the flash is so small that it's not affecting the human beings. And it turns out that you can actually transmit a lot of information that way. And so we've got a new sensing, a new communication modality. And people, particularly there's a group at the Technical University of Delft who are doing some really interesting, and there's another one at Edinburgh who are doing some really interesting research on looking at this as a communication medium. It's called appropriately SHINE. And finally, I mentioned that changing batteries was a pain. And so people, and this is one of the areas Lanny's working on, so maybe she'll say something about it afterwards, and that's energy harvesting. So instead of putting a battery in, maybe you could harvest the energy from solar energy, even solar inside, light energy inside, or temperature, or moving parts. So there's a lot of groups working on that possibility. And then you need to think about, well, if you're harvesting the energy, how do you build systems that use that harvestable energy? So I think that's an area where there'll be some great new developments. And if the nodes can harvest their own energy, then they start being able to look after themselves. So for example, that node I showed you at the beginning that we've transmitted on the farm, that's got 6 great big D-cell batteries in it. If instead they could harvest their own energy, then they could run forever. Whereas with the D-cell batteries, they ran out after a few years. And then we have to go and dig them up and change the batteries, which is not a good idea. Okay, so that's my look to the future. And I've got 2. These are slightly ethical questions, but one of them is it always good to gather more and more data? So I've told you man must measure and that it's a wonderful thing to do, but I think there's some places where it's not a wonderful thing to do and where we need to think about the risks of the technologies that we're building. And the other one, maybe more positive, is that I hope that's inspired you to think maybe of some new places, some new application areas where in the future there might be things we could do with these wireless networks that will make people's lives better and enable people to do things they can't do now, or maybe to do things they do now but better. So that's my questions for that section. This section. Again, let me open up the floor. Be brave and say something. We've got some questions. Great. The fault tolerance. Thanks very much, Richie. That's quite right. Yeah. You want to make sure it keeps running. So any thoughts about the future?
Yep. There's no. Anyone who would like to answer those 2 questions? Is it always good to gather more and more data? That means, does it have something to do with the privacy, Professor Rachel?
Yeah. How many of you would like in-body sensors collecting data?
There's one person.
That's exactly right, Ivandi. It's actually, and I think people are getting more and more aware of that as we have, so much data collected from our smartphones, from our computers, from everything we do. So the more data that's out there, the more possibilities that data might be captured or used for purposes that are not good, that we don't approve. So I think we need to be aware of that when we're building. That's good. Thank you for that answer.
Right. Thank you for the answer, Ifandi. For the second question, maybe? Or maybe you would like to...
Is anyone dreaming out there?
They're still
Go
dreaming.
on, dreamers. Tell me some dreams.
Yeah.
You're the next generation. You're supposed to be coming up with great ideas.
Yeah.
Throw something in the poll.
Right. One more answer, maybe from the floor, please.
Or question.
Or question. Yep. Well, actually, Professor Raja, I've got a question regarding the battery of the sensors. I was just about to ask about the battery issue, because once the sensor senses data from the environment, it keeps on transferring data to somewhere, to the sink perhaps. That would cause the battery life for the sensors. Would that be small device to harvest data? Is it from the sunlight or? Yep.
So there's different ways you can harvest energy. The sunlight is one. You can also do it even internal light has energy in it that can be harvested. in a car. So I have a car which harvests energy every time I brake or go downhill. So from movement, you can harvest energy. From temperature difference, you can harvest energy. So below the soil and on the surface of the soil, there can be a significant temperature gap. That gap can be used to harvest energy.
Right.
And you're right, it was good that you asked about the sending messages, because that does take up energy. And so another way is we can try and build our networks so they use the smallest amount of energy possible so that the batteries last for as long as possible. And with energy harvesting, you need to do that too. So you need to save energy, just like being at home, really. You need to save energy, but you also need to, if it's possible, to harvest the energy as well. That's even better. Oh, and there's also things like wave energy, water movement. So sensors in a pond could be used for that. Is there a technology that can prevent deforestation or forest fire? That's a fantastic question. Thank you, Vasa, because it's got two answers. And one is yes. So there are sensors that are placed maybe just below the ground or on the ground that can monitor heat and send a warning if there's a forest fire going through. But the problem with that is, if the fire's there, you're very unlikely to be able to send a wireless signal because the fire interferes with the atmosphere. And so my feeling about those is that they're only going to be able to detect when there's not a fire. And actually, you're going to lose signal as soon as there is one. But the other answer to that is this is a perfect example for those contactless sensing. So long-range infrared sensing, drones, so image sensing are probably better technologies for detecting forest fire. Deforestation, that would be a really good example for embedded technology, because maybe you get more light or something and you know there's a problem. But thanks for that question, because there's different ways of solving it. But you really need to think about it's a very challenging application area. Lani, ask your question.
Lani raised her hand. Please, Lani.
Hi, it's so good to see you.
This is like a small reunion of the
It's a reunion of PhD
PhD
students, yeah. Any other my students out there?
Yeah. All right. Please, Lani.
I have a question for your paper about the predictor, if I'm not mistaken. In that paper, if I understand, you only consider about the coverage. So what can a sensor sense, right? So they can predict the virtual sensor data. Do you ever consider about connectivity? I mean, for example, if our sensor network use energy harvesting technique, most of the time sensor has no power at all to transfer their data. So you expect to receive data from them, but they don't have power enough to send their data. So in this case, do you ever consider about connectivity?
That's an excellent question. In this particular framework, we were looking at the accuracy of prediction, and we were assuming you were using a technology like LoRa, where connectivity was not the main issue. But this research, in fact, earlier research than ours, they used in actually in your masters, and you may remember Babak Pazand also. There was a lot of work in looking at connectivity and where do you place the sensors to maximize the connectivity. So you're exactly right. That's another version of the minimum set cover problem. And there would be a very interesting version of that where you had energy harvesting and the connectivity is changing over time. So that was, yes, we did consider it, but it was out of the scope of that particular paper. We were looking at predicting the values, but that's another thing that needs to be brought into the equation. Great, thank you very much. Lovely to see you.
Thank you, Lani.
Sorry, it's lovely to see you all, but it's very nice to see Lani. I haven't seen her for years.
Right. We also have Annie. Annie, would you like to say something, Annie? Are you still here? She was also a student of the UWA. Yeah, any Uniarti?
Yeah.
Yeah.
Hello there.
Yes, I took my master degree at the University of Western Australia.
Excellent.
Yeah.
Good.
Yeah. She was a Amitava student.
Oh, very good. So has Amitava given his talk, or is he coming in the future series?
29th of October, 2 more weeks.
Excellent, because you're going to hear from him too, aren't you? Oh, that's great.
Yeah.
Good. Well, you're all a very good advertisement for coming to UWA, and I hope when the borders open up again that we'll see more of you.
Yeah, of course. All right. Any more questions, people? Or maybe answer to the questions? Yep. Yeah.
Okay. So I was just going to wrap up with a summary, which is I've talked to you about introducing what is a wireless sensor network, what are the components and why do we build them. I then talked about a specific virtual sensing framework for sensing, collecting the same information with minimal infrastructure. And finally, I hope that I gave you a little bit of inspiration for some of the future topics in wireless sensor networks and where this technology might be going in the future. So we've got, according to your 90-minute schedule, we have a little bit of time. If there are people have further questions, that's fine.
Yeah.
But that's it from me. Thank you very much for inviting me.
Thank you, Professor
I had fun preparing
Rachel,
this.
for the talk. Yeah, thank you for the talk, Professor Rachel. We've got our head of department, Pu Kastin Patika. Would you like to say something to Professor Rachel and the audience, please? Pu Kastin, are you there?
Shall I stop sharing?
Yeah, Pu Kastin. Yeah, she's got a meeting before we started our meeting. But yeah, okay, maybe Pak Ketut would like to say something before we wrap up our meeting today, please. He's the dean of our faculty, Professor Rachel. Yep.
Thank you, Pak Arif. First, I would like to say thank you to Prof. Rachel. It's nice to hear your talk. And actually, the wireless sensor network, IoT, and also right now we have a place for 5G connection and also research regarding those fields. It is nice to have a collaboration with you, Professor, because I would say that Indonesia is we have enough problem as a source for research, and also we have a source of funding actually from the university and also from government. We have a scheme called Cardell-Oliver. Maybe Pak Ari wants to set up the research to collaborate between university, industry, and also a partner from abroad, Pak Ari. So please, we can use this kind of scheme here. And also regarding the opportunity to receive our lecturer to continue study in your university, I would like also thank you very much. And I hope many research and many supervision, jointful supervision maybe can be set up ahead here. For audience, I will say thank you for following the talk from Prof. Rachel. Thank you very much, Pak Ari.
Thank you very much, Pak Ketut, our Dean of the Faculty of Electrics. Actually, we still have one staff studying under Mohammed bin Amun supervision, Professor Rachel. Her name is Wijayanti. Yeah, now we have Pak Munif, also one of our staff. He's looking for his PhD as well. Hopefully, he will join the family of UWA in the near future. All right. That is a wrap of our meeting today. Can we open our cameras, please, so we can have a group photo before we finish up our session today? Yep. There's 3 pages in my screen, so I need to take 3 times. Right, please give your best smile. Okay, I will start taking the screenshot in 1, 2, and 3 for the
Advancing
first
humanity,
page. Advancing humanity is the
our motto.
motto of our faculty. That's 1 page, and then second
Motto
page
of ITS.
is the motto. Idea, sorry. Second page is taken. And the last page is taken too. Alrighty, that's a wrap for today's meeting. Thank you all for coming, and thank you, Professor Rachel, for the talk. Very nice talk. That could be potentially attract students to research in the wireless sensor networks. For me, for myself, I would like to express my gratitude, and I'm sorry if there are some mistakes that I made during the course of the session. And we will see you again within the next couple of weeks with Professor Amitabh Datta from the UWA. Thank you and good afternoon, everyone.
Thank you all very much. Lovely to see you, and thank you for
very much.
organizing this.
Thank you.
Okay.
No problems.
Bye, everyone.
See you. Bye. Yeah, Lani.
Ivan.
Bye, Ivan. Yeah. I will end up the meeting in 3,